A light plane touches down on a runway that's too short. Engine off, nothing but momentum carrying it forward. Stretched across the tarmac ahead is a cable tied to a heavy sandbag. The hook catches. In a fraction of a second, the plane gets heavier and slower. Then it drags that sandbag to a halt. Two completely different kinds of physics back to back, inside one problem. The trick is refusing to solve them at the same time. Here's the whole problem. A light plane of mass 1000 kilograms makes an emergency landing on a short runway. Its engine is off and it touches down at 40 meters per second. Take that as its speed at the instant the hook catches. A hook on the plane snags a cable attached to a sandbag of mass 120 kilograms, resting on the runway, and it drags the bag along. The coefficient of kinetic friction between the sandbag and the runway is 0.4, and the plane's brakes supply an extra retarding force of magnitude 1400 newtons. How far does the plane travel before it comes to a stop? Set up coordinates before anything else. Let the x-axis point the way the plane is moving, let the y-axis point up, and put the origin exactly where the hook catches the cable. Now the structural insight that makes this trackable. It is really two problems. The snag is a collision. Plane and the sandbag lock together over an interval so short we treat it as instantaneous. The slide that follows lasts tens of seconds. Momentum handles the first stage. Forces and kinematics handle the second. Momentum survives the snag, even though friction and the brakes are acting the whole time. An external force needs time to change momentum, and we have assumed the snag takes essentially none. The external impulse over that interval is negligible, so the horizontal momentum of the plane plus sandbag system is the same immediately before and immediately after. Write both momenta. Just before, only the plane moves, so the system momentum is the plane's mass times its landing speed, directed along x. Just after, plane and the sandbag move together at one common speed, so the momentum is the combined mass, plane plus sandbag, times that shared speed. Setting the two equal gives the plane's mass times the landing speed equals the combined mass times the new speed. Solve for the new speed. It is the plane's mass divided by the combined mass, all times the landing speed. Put the numbers in. 1000 over 1120 times 40 meters per second gives 35.7 meters per second. The plane picked up 12% more mass and kept about 89% of its speed. That single number is everything stage 1 henceforward. Stage 2. The plane and the sandbag are now one object of mass, 1120 kilograms, moving at 35.7 meters per second, with two external forces slowing it down. Draw the free body diagram for that combined system. The runway pushes backward on the plane through its brakes. A horizontal force of magnitude 1400 newtons pointing in the negative x direction. The runway also drags backward on the sandbag. Kinetic friction also pointing in the negative x direction. Because the bag is sliding forward over the ground, gravity pulls the system down and the ground pushes up. Newton's second law along x reads minus the braking force minus the friction force equals the combined mass times the x component of the acceleration. Both retarding terms carry minus signs because both forces point backward, and that already forces the acceleration to be negative. The system is slowing, which is exactly what we want. The friction force is still unknown, so get it from the vertical direction, looking at the sandbag by itself. The bag has no vertical acceleration, so the normal force from the ground on the sandbag balances the sandbag's weight. The normal force equals the sandbag's mass times g, the gravitational acceleration. That mass is the sandbag's alone, not the system's. The plane's weight rides on the plane's own wheels and never presses down on the bag. And the cable pulls horizontally, so it adds nothing vertical either. Using the total mass here is the most common way to get this problem wrong. The friction comes out more than 9 times too big, and the stopping distance you compute is off by a factor of 3. Kinetic friction is the coefficient times the normal force. So the friction force equals mu sub k times the sandbag's mass times g. Numerically, 0.4 times 120 kilograms times 9.8 meters per second squared, which is 470.4 newtons. Add the two retarding forces. 1400 plus 470.4 gives 1870.4 newtons, pulling backward on the system. Divide by the combined mass. Negative 1870.4 newtons over 1120 kilograms is an acceleration of negative 1.67 meters per second squared. Every quantity feeding that number is constant, so the acceleration is constant, and that is what lets ordinary kinematics finish the job. Stage 2, second half, the kinematics. Two numbers come in. The speed immediately after the snag, 35.7 meters per second, and the constant acceleration, negative 1.67 meters per second squared. Measure time from the instant the cable goes taut, and the position from that same spot, so the initial position is 0. Velocity first. For constant acceleration, the final velocity minus the velocity just after the collision equals the acceleration times the elapsed time. The plane stops when the final velocity is 0, so the stopping time is minus the post-snag speed divided by the acceleration. The acceleration is negative, so that leading minus sign makes the time positive. 35.7 divided by 1.67 is 21.4 seconds. Position next. The displacement is the post-snag speed times the stopping time, plus 1/2 the acceleration times the stopping time squared. Substitute the stopping time into both terms and they collapse into a single expression. Minus 1/2 of the post-snag speed squared divided by the acceleration. Now substitute the acceleration we found. The stopping distance is 1/2 the combined mass times the post-snag speed squared, divided by the sum of the braking force and the friction force. That form has a clean reading, the kinetic energy the system carries away from the snag, divided by the total retarding force. Distance equals energy over force. One last substitution closes the loop. Replace the post-snag speed with the momentum result from stage 1. The stopping distance becomes the plane's mass squared times the landing speed squared, divided by twice the combined mass times the sum of the braking force and the mu sub k times the sandbag's weight. Every symbol on the right is given in the problem, apart from g, 9.8 meters per second squared. Now the arithmetic. On top, the square of 1000 kilograms times the square of 40 meters per second. On the bottom, twice 1120 kilograms times 1870.4 newtons. The result is 382 meters, which to two significant figures is 3.8 times 10 squared meters. And notice what that distance is measured from. It runs from the point where the hook caught the cable, not from where the wheels first touched the runway. The landing roll before the snag is a separate question this problem never asks. Step back and look at the shape of the solution. One problem, two stages, two different laws. The snag is fast. Over a vanishing interval, the external forces deliver vanishing impulse. Momentum is conserved, and the whole stage reduces to a single line of algebra. What the brakes and the friction were doing during that instant simply does not matter. The slide is slow. Now those same forces have all the time they need. Momentum is emphatically not conserved, and the Newton's second law with constant acceleration kinematics carries the system to rest. One number bridges the two stages, the speed immediately after the collision. Stage 1 produces it, stage 2 consumes it. Nothing else crosses the boundary. Conserve momentum across the fast interaction, then analyze forces over the slow phase that follows. That pattern is the backbone of almost every collision problem you will meet. Identify which stage you are in, and the right tool picks itself. To practice what you just learned, this course has free exercises and AI-graded feedback on ludium.ai. The link is in the description.